Today, I will be presenting the abstract of our project, the Intelligent Water Pump Controller System. This project focuses on solving major issues in traditional water tank management such as overflow, pump dry running, and the need for constant manual monitoring. Our system uses 5 water level sensors connected to a PIC microcontroller together with LED indicators, an LCD display, and a relay driver circuit to control the pump automatically. We designed the hardware in Proteus ICs, programmed the control logic in C, and added interrupt routines so the system can react quickly during critical water level changes. From the simulation, all tank levels were detected accurately, the relay switched reliably, and the system responded immediately when sudden changes occurred. Overall, the intelligent controller proved to be an efficient solution for automated water management, with strong potential for real-world use and future upgrades like IoT monitoring.
Hello everyone, let's talk about something we all use every day but might not think about it, which is our water tank. First, why it is so important. Think of it as water savings account. It saves water to use at home, on farms, and in factories. It is especially important when there's no water from the main pipe or when the water pressure is very low. But here's the big problem. Bad control. If we don't control our water level in the tank properly, 3 bad things happen. First, we waste a lot of water when the tank overflows. We get very high electricity bills because the pump works too hard and the pump can get broken if it runs without water. So what is the smart solution? The smart solution is we need to upgrade to an automatic system that uses a computer chip, which is a microcontroller. Why? Because research shows that the smart system can reduce water waste by 35%. The benefits are very clear, which is prevent waste and save money, reduce energy use, protects pump equipment, and enable real-time monitoring. Next, the old way of controlling the water tank has 2 major flaws. The first one is overflow. This is when the tank gets too full and water spills out. This is very serious waste. A study found it causes 15 to 20% of home water waste. The spilled water can also damage your property and the ground of the tank. The second problem is dry running. This is even worse for the equipment. It happens when the pump turns on, but there's no water to pump. The pump gets very, very hot, very fast, and this permanently destroys its motor and seals. Fixing or replacing a pump is very expensive. Why do these problems happen? It is because the oil method, checking manually or using a simple float switch, is too slow or often fails, and maybe depends on us to not making mistakes. We easily forget to switch on or switch off the switch. So, the solution is very clear. We need an intelligent automatic controller. This smart device will automatically stop overflow and prevent the pump from dry running. It saves water, protect the pump, and give us peace of mind. This brings us to the goals of our project. Next, the project objective is to design and simulate an automated water level monitoring and control system using Proteus ISIS that prevents tank overflow and pump dry running conditions. Next, to implement a control algorithm using interrupt techniques for immediate response to control water levels, ensuring pump reliability and safety. Last, to integrate visual LED indicators for clear display of both tank levels and status, which is empty, low, half full, and overflow, and also pump operational state.
Hello, I'm Nurida Hidayah. I'll be presenting on our methodology section, and I'm going to start with our approach. Firstly, we do a system study. This is where we do our requirement analysis. We see what we need. We check what indicators that we need to have in the system and identify like the water level states are required, which is empty, low, half, full, and overflow. And then we check for a safety requirement, and we decided that it needs no dry run, no overflow, and a continuous monitoring of tank levels. Then after we have do our system study, we go for hardware design. For hardware design, basically we connect the wires, place our components in Proteus, and then make sure our resistors are having correct values, our capacitors, everything has correct values, and the connections are making sense. At first we have sort of like, we are unsure what to connect, what the circuit needs to have. So in the next slide, there will be a reference which gives us an idea on what is needed in our hardware system. And then after that, we do our software development. This is where we code our code in C inside PCW compiler, which is going to turn that C code into an Intel hex file, and then which is later going to be used in our integration, where we integrate our PCW code that is turned into Intel hex file into the PIC microcontroller. We use PIC 18F54500 for this project, and then we do testing. If it's working, we take our results. If it's not working, we're just going to start from the hardware design. We try to see what is going wrong. Okay, this is the reference section. You can see on the left is a GitHub project, and on the right is a paper I found on ResearchGate. And on this left, it's basically the same thing we are doing, but without the switches, because they use actual ultrasonic sensor, and they code the sensor with Arduino code. Initialize ports and LCD, and then we give a value of 0 to pump, showing underscore data, and timer underscore counter, and now we read any underscore button, basically checking if any buttons are pressed. So if there's button pressed and the underscore button equals to 1, which makes it true, it will check if there's any data shown. So if there's no data shown, it will proceed to determine level and update LED based on level, and then check pump logic. If the level is full or overflow, the pump will turn off, and then if it's half, low, or empty, the pump will be turned on. and then it will give an output, which is the pump. It will pump, and then the relay, and then the pump LED is also going to be the output, and then there will be output on LCD, which makes it show level, and then show the pump, and then show debug character, either E, L, H, F, or O. And then when that's done, we go back to the beginning where it reads any. Okay, now we're going to look at the block diagram, so we can see that the power supply is supplying power for both microcontroller and water level sensors, which is 5 volts for each, and then when there's an input from water level sensors, it's going to the microcontroller, and then this microcontroller is going to like produce a logic which makes an LCD display, and then there's the pump relay, and then pump LED if it's showing or not, if it's working or not based on the logic, and then it will show LED for tank levels if there's any based on the logic. And then if you can see the arrow inside the microcontroller is showing the loop.
Hello dan selamat sejahtera. I am going to present how this circuit works, how this fully automated pump works. So, starting with the simulation, it will show as a default the water tank control. So when it is empty, the pump is on, and you can see that the motor is running. And then, this is at an empty state. And then, it is at a low state. The pump is still running, and you can see like the indicators of the LEDs that the water is low. And then, when the tank is full, the pump will turn off, and thus it stops the motor. There is another mode where when it is half, the pump is still turns on. It's still turned on according to this yellow indicator and the motor running. And then there is this one, overflow. When it overflows, the pump will turn off immediately and the smart sensor will detect it. And thus that is how the water tank functions. That is all. Thank you.
From the simulation, we can see that the intelligent water pump controller system performs exactly as designed. The 5 water level sensors successfully detect each stage of the tank: empty, low, half, full, and overflow. And the PIC18F4550 microcontroller responded with the correct pump actions. This shows that the control logics work well and consistently. The LED indicators also help clearly show the tank status in real time, so we could easily observe the system behave when the water level changes. One key highlight from the simulation is how fast the interrupt routine reacts. When the tank suddenly reached a critical level like empty or overflow, the system responded immediately without delay, which is something traditional float switches cannot do. The relay driver circuit also operated smoothly, switching the pump on and off in a stable and safe manner. Overall, the simulation results prove that this intelligent controller can reduce the risk of overflow, prevent dry running, and make the water system more efficient and reliable. This shows that the design is practical and suitable for real-world application. In conclusion, the intelligent water pump controller system clearly achieved the goal set for this project through the use of digital sensors, interrupt routines, and relay switching. The system is able to monitor the tank continuously and make accurate pump decisions without human intervention. The simulation results shows that the system can successfully prevent the two major problems, water overflow and pump dry running. By stopping these issues, the system helps reduce water wastage and protects the pump from damage, which makes the entire water management process safer and more efficient. Another important point is that this design is very flexible. It can be upgraded in the future with features such as IoT monitoring, mobile alerts, or more advanced sensors to improve accuracy. Because of this flexibility and strong performance, the system has the potential to be used not only in homes but also in agriculture and industrial applications. Overall, this project provides a solid foundation for building a fully intelligent for modern water management solution. Lastly, I will explain the references used in our project. For this system, we referred to several academic papers, online resources, and an open source project to support our design approach. The first reference is a study by Izunongo, which discusses a microcontroller-based water control system. This paper helped us understand how automated water level control can reduce water wastage and improve pump management. The second reference by Sen and colleagues focuses on water level control with dry run protection. It provided insight into the risks of pump overheating and the importance of safely logic in pump operations. We also referred to an open-source GitHub project by Ratul, which features an ultrasonic-based water monitoring system. Although our design uses float sensors, the repository helped us compare different sensing approaches and control techniques. Finally, we used a conference paper by Abdelati and Frey on smart domestic water management systems. This reference supported our understanding of PIC microcontroller applications, system structure, and smart control strategies. Overall, these references strengthened our design decisions and validated the techniques used in developing our intelligent water pump controller system.